Okay, so hello and welcome to the ACigs webinar series today on Thursday, the 17th of February, 2022. My name is Ryan Hackney and I'll be hosting today's webinar. ACigs is the Australasian chapter of the International Geosynthetics Society and has been established for 20 years. We are one of the 45 chapters globally, which combined have over 4,000 individual members, over 500 students, and includes more than 190 corporate members. The Australasian chapter covers the interests of Australia, New Zealand, and the Pacific Islands. By becoming a member of ACigs, you also become a member of the IGS, and there are many resources available directly on their newly updated IGS website. This includes educational documents, lecture series videos, a library of previous IGS proceedings, and access to geosynthetic technical journals such as Geotextiles and Geomembranes and Geosynthetics International. You can access the website at geosyntheticsociety.org, or you can use the QR code in the bottom right-hand corner of the screen. In addition to this, we have our own ACigs website, and this also contains many of our own resources, including a dedicated student section, current ACigs news, information on upcoming events, and information on how to become either an individual member or a company member. Our own resources include all of the previous webinars that we've recorded to date, plus other events that have been recorded, such as our seminar series and our technical committee forum debates that we introduced last year. If you've missed any of our webinars, the recordings are available free to access in the resources section of our website. If you would like a certificate of attendance for today, if you could email us at info@acigs.org with your information, we will be able to email back a certificate for you. And this is just a quick reminder of our upcoming Geosynthetics conference, GeoANZ, that will be held in Brisbane between the 7th and 9th of June this year. The early bird registrations are open and the extended abstract deadline is approaching on the 28th of February. And moving on to today's webinar, we have a very special guest, Professor Jane Rickson from Cranfield University in the UK. She'll be sharing her work on soil erosion and conservation using geosynthetics. Jane Rickson is Professor of Soil Erosion and Conservation in the School of Water, Energy and Environment at Cranfield University. Trained as a geomorphologist, she specialised in land resource engineering and management at MSc and PhD. She has over 35 years experience of research, consultancy and teaching in soil and water engineering, specialising in soil degradation processes such as soil erosion and sustainable land management. Her work is dedicated at industry and policymakers at the local, national and international levels. She has published widely in international peer-reviewed journals, conference proceedings and trade articles. She is a fellow and past president of the Institution of Agricultural Engineers, a chartered environmentalist, fellow of the Higher Education Academy, and member of the Institution of Professional Soil Scientists. So please, if you have any questions, if you could write them in the Q&A section with your name, and if we don't have a chance to get to those at the end, we'll be able to get back to you. So thank you, and I would like to now welcome Jane to present today's webinar. Thank you, Jane.
Thank you, Ryan. Thank you very much. Good morning, everybody, and greetings from the UK. It's 5 minutes past midnight. That shows how dedicated I am to geosynthetics, that I've stayed up all night long, almost. But anyway, good morning, everybody, and thank you so much for inviting me. I'm just going to share my screen, hopefully the right one. Can you see that okay?
We can, thank you.
Good, okay. I just need to bring it onto this screen. So is it in presentation mode now? Yep. Okay, very good. Right. Well, good morning, everybody, and thank you again for inviting me to speak today at the webinar, and greetings from the UK. So thank you very much, Ryan, for that introduction, that very long-winded introduction. Sorry about that. So yes, my name is Jane Rickson. I work at Cranfield University in Bedfordshire in the UK. I have literally a minute ago changed the date because I put the 16th, because it is kind of just the 16th here, but it's the 17th where most of the people on the call are. So I've put the 17th, but I'd like to share some of the work that I've done using geosynthetics for a very specific application. And I know geosynthetics are used for many different applications in construction world, in industry, but I'm going to specifically be looking at soil erosion control and soil conservation using these products. So what I'm going to try and cover in the next 40 minutes or so is I'm really sorry, but go back to school sort of basics about soil erosion processes. And my excuse for this is that it really does help to understand those processes of soil erosion, to help evaluate the effectiveness of different geosynthetic products for erosion control. And I think I'd also like to show that knowing those processes also help us to design and specify the most appropriate product for a given application. So apologies for those of you, I'm sure many of you are experts in soil erosion, but I'd like to go back to basics and then build on those foundations to then start talking about evaluating and designing new products for erosion control. I'd then like to look at rates of soil erosion and the consequences of soil erosion. In other words, why do we bother to do anything about erosion? Why should we bother using these products? And then I'd come down to the specifics about the role of geotextiles specifically in soil erosion control, a little bit about the work that we've done at Cranfield for now, yes, 35 years or so, testing some of these products and providing evidence, quantitative evidence, to designers, manufacturers, specifiers, contractors, whoever that might be, as to whether these products work or not, and why they work or not. And then if you've all fallen asleep by then, or maybe I've fallen asleep, given it's 5 past midnight, but if I've fallen asleep, then right at the end, there are some take-home messages that I'll hopefully wake you up for those take-home messages. So hopefully this will be of interest to everybody on the call. So forgive me for going back to, as I say, school days in terms of soil erosion, but I will make the point that understanding these processes does help us to design and specify the products that we're going to use to control these processes. Soil erosion, the definition of soil erosion is the removal of slope-forming materials by erosive agents, be it rain splash erosion, that very first individual raindrop falling on the soil surface, imparting its kinetic energy, which then detaches and then transports those particles once they're detached. So we have rain splash erosion, we have interrill or sheet erosion. That's before the overland flow starts to concentrate. Then we have rill erosion and then gully erosion getting more and more severe. There are other forms of erosion as well: subsurface erosion, wave, shoreline, riverbank, wind erosion, mass movements. All of these are also processes of erosion, but I'm not going to focus on those so much as surface erosion, topsoil surface erosion, just in view of the time that we have to talk about these things. So I'm mainly going to be talking about surface erosion processes and the products that are used to control it. So again, if we look a little bit about the processes, then it is a cyclical, it's a natural process, but it's often aggravated by the way in which we manage land, we use land. Often in a construction site, we're taking away the vegetation, we're exposing the bare soil to rainfall. And that's where we have a high window of risk of soil erosion. And the first phase of soil erosion is the detachment of the materials from the soil mass. This might be from the rain splash impact, as I say, that individual drop falling on that bare soil with its kinetic energy is able to then detach particles and then transport those particles. But the first detachment could be by rain splash impact. It might be by overland flow or runoff if it gets sufficient shear stress to actually detach material. And then, of course, wind erosion. Again, I'm not going to be talking about wind erosion today. Once you've detached those particles, that's the very first process. And I would argue that if you can control that very first process, then you won't have any erosion, which is exactly what we're trying to achieve. But if we don't control that detachment process, then those particles become entrained, either in the rain splash jets as they splash away from the point of impact, or they're entrained in the overland flow that's running across that soil surface, or, as I say, in the airflow. And then we will transport those eroded materials, those detached materials, again in the rain splash jets, not very far distances, but more importantly, where you have overland flow, you have surface flow, then all of that detached material is then transported. Further down slope, that material may be deposited. It might just be dropped at the bottom of the slope, and you'll see there a photograph of some work that we're doing. Okay, it's in a potato field, but even so, you can see the amount of erosion and the amount of deposition that's taken place. And the point, why am I talking about erosion processes in a talk on geosynthetics? My argument is, where is the most effective place to use erosion control products? And I would argue it's this very first stage. If we can control that detachment, we don't need to worry about entrainment or transport or deposition, because we've headed it off at the pass, so to speak. We've controlled that at source, rather than letting that eroded material get into the pathways and into the receptors. So I would argue that's where we should be using geosynthetics, geotextile products, to control erosion. But why would we bother with soil erosion? Is it really that much of a problem? And I just want to present some data on the rates of soil erosion that really justify the use of these products. So here you'll see various projects that we've been working on in construction projects, where obviously you've got that window of very high soil erosion risk after you've done the land forming, after you've done the landscaping, and before you've got vegetation established. There is a very high window of risk because you've got bare soil that is susceptible to this rain splash detachment and runoff and so on. And this is the point at which we should be using some erosion control products. And again, if you look in the literature, you can see just how high those rates of erosion can be on these newly constructed, unprotected sites. So again, I've just gone through the literature. These are a bit old. I'd like to call them classic rather than old, but they are a bit old now. But anyway, but you can see the rates of erosion on some of these mine spoils, tailings, for example, construction sites, highway embankments and cuttings and so on. And these are very, very high rates of erosion associated with those constructed sites. It's hard to visualize exactly how much soil is being moved, but if you then compare it with the soil loss tolerance, so how much soil we can tolerate to lose, it's been estimated that should be about 1 ton per hectare per year. That's the US EPA, Environmental Protection Agency, and indeed in Europe we've done some studies that identify that that is the soil formation rate. So as soon as you exceed those soil loss tolerance rates, then you're getting problems in terms of the damage that's been done to the environment, and therefore the need for these products. Now, I said those data were rather old and out of date, but there is a big issue about climate change and extreme weather events likely to cause even more rates or even higher rates of erosion in the future. And so that's something that we need to look out for. And again, to justify the use of these products because of these very extreme weather events that are going to cause more erosion. There's a lot of literature that demonstrates the correlation between extreme weather events and soil erosion. So again, just as background, why would we bother doing anything about it? You know, of course she would say erosion is bad, it keeps her in a job. Of course I would say that, wouldn't I? But it's not just me justifying my existence, but there are serious consequences of that occur of soil erosion, which again justify the use of these products. So as an environmental engineer, I'm worried about erosion because it's first of all getting rid of the very precious resource, natural capital I need to start to reclaim those sites to get vegetation established. So if I'm allowing erosion on a particular site, then I'm getting rid of all my rooting media where I'm going to get my vegetation establishing. I'm preferentially removing nutrients because the nutrients tend to be absorbed onto the particles that erode most quickly. I'm going to lose any seeds or seedlings that I've got. They're going to be washed away with the erosion. Any agrochemicals I might have applied, any organic matter or soil carbon, again, we know this is preferentially removed. Impacts on microbial communities, loss of trace elements, loss of your water holding capacity, particularly during droughts and so on. And of course, it may cause really serious problems in terms of infrastructure foundations. And I would argue soil erosion is irreversible. Once it's gone, it's gone. The rates of soil formation are so slow and so low, it's impossible to get that soil back. But actually, it's not those on-site impacts that are of particular worry. It's where all that erosion goes, where all that eroded soil goes. And again, forgive me for giving all of this background, but it's really to try and make the case of why we need erosion control products, which I will come on to in a minute, I promise. But it's those off-site impacts, particularly to do with water quality. All of that soil, all of that sediment is going to end up in your river courses. And that sediment is going to be carrying pollutants and contaminants, and it has all sorts of ecological impacts on your water courses. Water temperature changes, dissolved oxygen levels change, the depth of light penetration, etc. This is going to have ecological impact on your water courses. So it's not only where the erosion occurs, it's the off-site impact of that erosion. Funnily, you know, things like angling, you know, that is a huge impact in terms of effect on fisheries, for example, by having all of this sediment, which could be controlled at source by using geotextile products. And then again, off-site, we've got sedimentation somewhere. All of that soil is going to be dumped, and it's going to be dumped in our channels, which reduce the capacities of those channels, increasing flood risk. I've mentioned ecological impacts, big impacts on salmon fisheries, for example, and then somebody's got to get rid of all of that sediment, and that's going to have a cost associated with that. And it's so frustrating because all of this could have been prevented by better erosion control on site. I love this quote. This quote to me justifies the use of soil erosion control measures. It costs less to keep soil on the land than dredge it from water bodies, hence the philosophy of control at source for water pollution by sediment. And that's exactly where I think geosynthetics, geotextiles have a role to play. So let's now start focusing on the work that I've done on geotextiles and how they're used for erosion control. A lot of my work uses this stuff, vegetation. Love vegetation. It's really, really effective at controlling soil erosion on sites. We know that vegetation is really good at intercepting any rainfall. It then stores a lot of that rainfall within the canopy of the vegetation. It breaks up the size of the drops into these shattered raindrops that have lower kinetic energy or erosivity to cause erosion. We've got lovely roots adding to infiltration. Fantastic stuff, brilliant. But it doesn't happen overnight. We won't get vegetation established on a newly constructed site overnight. We need time. We need time to get vegetation to be effective, maybe 60% canopy cover. We need the stem density to intercept any overland flow and impart roughness to that flow. We need the dense root network to encourage infiltration. So it's this window of high soil erosion risk, which is where we need these geotextile products to control erosion immediately. So geotextiles for soil erosion control, and all of you on the call, I'm sure, will know the definition of geotextiles, that these are permeable textile materials used with foundation, soil, rock, earth, or any geotechnical engineering related material. And again, many of you will know that this is not a new technique. Using these textiles in the construction industry and not a new technique. They can be dated right back to ancient Egypt. I wasn't around then. For example, the use of cotton to reinforce building materials. A lot of the textiles were also used in World War II to create, for example, artificial airstrips, landing strips. But the use of these textiles particularly increased in the 1960s because of the availability of cheap synthetic textiles, technology developments there, and that was married serendipitously with, there's a good word for today, serendipitous, I can't say it again, rapid urban and infrastructural development and expansion. And those two things collided, whereby there was the availability of textiles and this rapid urban development. And obviously in present day use, we're now using more environmentally sensitive products, and certainly has implications for world trade and economic development. A lot of the products I'm testing have come from developing countries, coir, jute, sisal, and so on. And again, those markets for those products obviously support rural livelihoods and local economies, which is very, very important. The fibres that are used for geotextiles for soil erosion control, again, I'm sure many of you are familiar with these, but many of you, I'm sure, will be using synthetic products rather than natural products as well. The natural products tend to be only used in soil erosion control, although we have done some work on rural road stabilisation using some natural fibres, but I'm not presenting that work today. So the fibres that are used can be woven or non-woven or knitted for erosion control, and they're found in the form of mats or webs or grids or sheets. They can be 2 or 3 dimensional, and as I mentioned, they can be natural versus synthetic. And I think this application of erosion control does lend itself to natural products. And again, I'll show you some of the product evaluation where we've compared natural and synthetic products. And again, it's interesting, it's really interesting, the different mode of installation. Some of these products, the installation recommendation is for them to be buried, and other products are just simply laid on the soil surface. It's interesting, some products, the same product in the US is recommended to be surface laid, and in Europe, the same product is recommended to be buried. So it's obviously quite a movable feast as to the specifications of how these products are actually used. If we look at some of the natural products that we've evaluated, the materials are things like wood fibre and straw, coir, jute. The more marginal ones, again, we've worked on things like cotton, wool, paper, needlegrass, seaweed, borassus and burrito, palm leaves, sisal, banana leaves. The best gig I ever had, it probably in my career, was that I was written to by the Caribbean Board of Science and Technology some years ago, who wanted to diversify the use of banana leaves. And they wanted to sort of diversify the banana industry, and they wanted to find alternative uses of banana leaves. And they wrote to me to ask me whether banana leaves had any potential as a natural fibre erosion control mat. And I did my homework, and I was very good, and I looked it up as to the properties of banana leaves, and they really would not make a very good erosion control product. They don't have very high absorption, and it would be very difficult to use, and they don't have very good drapeability, which I'll talk about in a minute. And so I wrote back to them and I said, that's right, they'd invited me to a conference in St. Lucia, all expenses paid, to the Caribbean, to St. Lucia, and, you know, come and tell us about how fantastic banana leaves are. And of course, I found out that they're not going to be very good. So I wrote to them with a heavy heart saying, I'm really sorry, I can't come to your conference because banana leaves are not suitable as a geotextile because of the research that I've done. They said, nah, never mind, come to the conference anyway and tell us that. And so I got a free, all expenses paid trip to the Caribbean to say that banana leaves sadly are not a very good geotextile for erosion control. But what a great gig that was. Fantastic. Thank you, Caribbean Board of Science and Technology. All right, okay, so natural fibers, they can be biodegradable, they can be light degradable, and therefore the argument is that they're environmentally friendly. There are claims that they add organic matter because they're made of organic materials. As they degrade under light and biological attack, then that organic matter becomes available to the soil, making the soil more fertile and giving a substrate for microorganisms within the soil and earthworms and so on and so forth. So there may be beneficial soil biology effects. I've not seen much research on that, and I'd welcome if anybody does know of any research. It's something we could carry out, but just never got round to. There's also all sorts of claims from the manufacturers that they add nutrients. There's certainly an argument that I think aesthetically they're more pleasing than some of the synthetic products, but beauty is in the eye of the beholder. But they certainly seem to blend in better with the landscape. They tend to be cheaper in terms of cost, but of course they are temporary. So you've got to get that vegetation established in the long term. And then the sort of synthetic products, again, many of you will know this already, but specifically for erosion control, the products available, polypropylene, nylon, polyester, polyethylene, so on. And of course, these are permanent because they will resist acids and microbiological attack and so on and so forth. And there is a question as to whether they work, these synthetic products work with vegetation as a synergistic erosion control, whereby you get the control from the vegetation and the erosion control from the geotextile, and you actually get a synergy. You actually get more erosion control by combining those two components. There is some question about aesthetics. Again, beauty is in the eye of the beholder, but let's face it, they don't necessarily blend in with the landscape. And frankly, and again, I'm sure there'll be manufacturers on the call, but I've seen some manufacturers have tried to dye these green, but they look so unnatural green. And again, I'm going to get it in the neck for that. But you know, by dyeing it, it doesn't always help for them to blend into the landscape. And finally, they are quite costly, and I'll come back to that point about cost in a minute. So I'm going to now sort of focus on the work that we do on performance testing of all of these products, because when I started this research, there was very, very little quantification of how the different products on the market actually work. To what extent do they work, and how do they work? And I was really concerned that a lot of specification of these products was really just because John uses it down the road, so I'm going to use it as well. And I thought there needs to be a more scientific basis to specification and indeed design of these products. So that's really why we set about trying to get some quantified, scientific, robust data behind how these products work. So do these products actually work, and how do they work? How do they change those erosion processes that I mentioned? And I think this is really important because I think it will inform the specification, what product works best where and when, to help contractors select the most appropriate products. And also, I hope that this research is useful to manufacturers who can come up with designs of new products that will be even more effective. So there are some slides there, some photographs there of some of the experimental trials that we carry out the evaluation, be it in the field, or be it in our rainfall simulation lab, or be it out the back of our lab where we have, again, a rainfall simulator to simulate different rain events. The original work that we undertook looked at 7 different products that we believe were representative of products at that time. And really not many have changed in terms of the principles behind the products available for erosion control. So we had a mixture of natural and synthetic products. Some were surface laid and some were buried. and they had a range of prices. We thought cost was really important, particularly for people who are specifying these products. So you'll see these product names, and yes, many other geosynthetic products are available on the market, but these were representative of the products when we first started this experiment. So you'll see the different product names and some description of the different materials. So we had a mixture of synthetics and natural, as I've mentioned, different weights, different area of geotextile, and different modes of installation. Now, these very first, you'll wonder, why have we got such small target areas where we're testing these geotextiles? And that's because we broke down the erosion processes into those processes that I mentioned early on. So we asked the question, how are these products performing under rain splash erode? Remember, I said that detachment, that very first detachment process, is the most important for erosion. So why don't we evaluate these different products and how effective they are at controlling that very first raindrop hitting the soil surface, because that's where most detachment takes place. So the experimental trials that we carried out, we used our rainfall simulators, 2 examples of a rainfall simulator. This is our hypodermic needle rainfall simulator. There's 900 needles, all producing drops of a given drop size, which can then be broken down into a random drop size that we would get under natural rainfall. Those fall under gravity. We have a rain tower that's about 9 meters high to allow those drops to reach their terminal velocity, and knowing their mass and knowing their velocity, we can calculate the kinetic energy of those raindrops. Or we have our nozzle rainfall simulator, which has pressurized water being forced through a nozzle of known geometry that will then again produce a nice uniform cone of rainfall and of random drop size distribution, but again with kinetic energy that is similar to natural rainfall, so that we can simulate this raindrop impact on the soil surface. We thought it would be interesting to look at different soil types. Does that affect how these products perform? We thought it'd be interesting to look at different rainfall intensities. Would that affect performance? The storm duration, the storm return periods. Is this product going to be useful for a rather boring 1-in-1 year storm, the storm that we get every year? Or can it cope with some of these really extreme events, these very high rainfall intensities that we are seeing to be the norm? And different storm energies, I mentioned kinetic energy. And what we could do from this test is then to compare the total detached material from those different products, from those splash cups. And the reason that they're so small is that we didn't want any overland flow generated. We just wanted to look at that raindrop impact, that rain splash process, without any overland flow, surface runoff being generated. And here are the results. Very surprising. Well, surprising and not surprising. So you can see here we have the control. This is the bare soil control with no geotextile protection. And you can see that the blue is the high intensity rainfall and the burgundy is the low rainfall intensity. I've only presented the sand results again in the context of time, but happy to share the clay results with you if that's of interest, to look at the differences in the soil type on performance. And we found that the natural products, so the geojute, the fine geojute, the enviromat, and the Bachbeck-Gewebe, which is the coir product, and indeed the encamat, which is a nylon product, surface laid, the S stands for surface laid, all were very effective at controlling soil loss relative to the bare soil control. What we were very surprised at is that at the high rainfall intensity, the buried products, the encamat and the tensile mat, buried products, gave soil loss higher than we were getting in the control. And that was very, very surprising and a little worrying. So the relative product performance was better under the high intensity rainfall. So that implies that geotextiles work better under the high rainfall intensities. The natural products perform very well, as I've mentioned, but this rain splash detachment from the buried geotextiles was greater. And we think that's because by burying the product, you're effectively sieving the soil, you're breaking any soil aggregation up, making that soil within the geotextile very, very prone to rain splash erosion. And that's why we were getting more erosion. Now, hopefully that would be compensated when we come onto the runoff test, where we do get runoff, that runoff will then infiltrate into that loose backfilled material. And I'll come on to runoff tests in a minute. In conclusion, for the rain splash test, what we found is that we could then correlate geotextile properties to the performance of the different products. So we found things like, not surprisingly, percentage cover was really, really important. The more coverage of the soil, then the less the erosion. Well, that's pretty obvious, isn't it? But we also found things like thicker fibers worked very well because they could intercept any rain splash that did occur, was then intercepted by the thicker fibers, and indeed the rougher fibers were able to collect any rain splash material. Certainly the surface laid worked better, and the products that had a high water holding capacity were able to keep the soil drier for longer because they absorbed the rainfall, and that meant that the erosion rate was less as well. So just by that really simple experiment, really useful insight as to how the different products, the different properties of the products perform. So we thought, okay, that's rain splash. Let's now have a look at runoff and how these different products perform where we've actually got surface overland flow, which is much more realistic to field conditions. So again, we had our rainfall simulator applied onto our large erosion rigs, our runoff rigs, that can be tilted at different gradients. The rainfall is then applied. You can just see this black mark here. This is our tracer where we were measuring the velocity of flow. In this case, I think it's a jute product that we then installed on the soil surface. And we can measure the runoff, the surface runoff, and any sediment in that surface runoff at the bottom of the slope. And we also were measuring infiltration because we were interested to what extent these products held up the water on the slope, allowing infiltration. So again, we had our two soil types because we thought soil type might affect the performance of the products. We had a constant runoff rate. And we ran the test for 10 minutes to represent a sort of quite erosive storm. And we're starting to collect much more data. So we could collect data about how much surface runoff or overland flow was generated with the different products, how much infiltration occurred, how much leachate we got from holding up the moisture on the slope itself, the soil loss, the sediment load, and then the sediment concentration in the runoff itself. And this was a surprise as well. So we looked at, this is just runoff. This is just the amount of water that comes off the bottom of that slope. And you will see that there's hardly any difference in the amount of runoff. Now, we were really surprised. We thought the natural products would be like little sponges and would absorb all of that runoff, but indeed they didn't. And in fact, if anything, some of the woven products, particularly the warp fibers, actually wicked more runoff going down the slope, which is why you can see slightly, it's not significantly statistically different, but the geojute, for example, and the fine geojute actually increase the runoff volume because of this wicking effect, this channeling effect of the runoff. So all treatments yielded similar runoff volume. We were very surprised. We thought they would absorb, the natural fibers would absorb, but that didn't seem to be the case. And even the natural products that had a high water holding capacity didn't reduce the amount of runoff. It didn't matter whether you put surface or buried. You know, my theory that if you've got buried products, you'd increase the infiltration. That didn't seem to be the case. Although again, the tensile mat did increase infiltration with less runoff, but again, quite a lot of variability around that. And we found that runoff velocity and the roughness imparted to flow as expressed by Manning's N did vary quite a bit between the treatments. And that last point helps to explain what we saw when we looked at the soil loss within that runoff. And here are those results. And again, quite surprising, the difference in the amount of soil loss that occurred from the different products, given that runoff had been the same for all of them effectively. The good news is that they all reduced soil loss compared with the bare soil control. So even where we had the buried products that had higher rain splash erosion, when it came to runoff, they were able to control the erosion as well compared with bare soil. The best erosion control was given by the woven products, particularly the jute products, and they were yielding only about 15% of the sediment coming off the bare soil control. At this scale, the mode of installation, whether you're surface or buried, had little effect on those soil losses. And again, we correlated the performance of these products with their attributes, with their properties. And we found that the soil loss control was explained by things like the geotextile induced roughness, the ability of the product to impart roughness to the flow. The flow was so busy overcoming that turbulence and that friction that it lost any energy to then detach and transport the particles of soil. So we found that geotextile induced roughness really important. We also found the ability to increase the flow depth through surface ponding helped to protect the soil from rain splash, adding a sort of buffer effect where you've ponded that water, the rainfall fell on the water and didn't actually hit the soil. We did think high water holding capacity was important because it increased the weight of the product. Not so much that it stopped the runoff, but it made the product very heavy, which means you had very good contact between the product and the soil, which then also led to this high drapeability or huggability, as somebody called it once, which I thought was rather sweet. Huggability, the ability of the product to hug the soil surface, was also very important to explain performance. So we thought, oh, well, why don't we correlate these geotextile properties that we thought would be important in affecting their performance? And we correlated those properties with soil loss. And you can see, not surprisingly, things like area of the geotextile, the depth of flow I mentioned, the Manning's roughness coefficient, the water holding capacity, the weight of the product when it was wet. All of these were significantly correlated with soil loss. They really explained the soil loss that we observed. But it was also interesting to see there was no correlation between cost and performance, which is quite interesting. So in fact, some of the cheaper products actually outperformed some of the more expensive products. And we also found, and I really want to come back to this point, that tensile strength was also not significantly different, did not explain the soil loss. There was no correlation between tensile strength of these products and their ability to control erosion. And that's really, really important because I think a lot of specifications require tensile strength. And whilst that's important for installation and carrying the products to the site and rolling out the products, once they're installed, tensile strength has nothing to do with the erosion processes operating in the way that I've described them, detachment and transport. You don't need high tensile strength products to control erosion. So I think that's important for specifiers, that they don't put tensile strength as a showstopper if you don't meet the tensile strength required. All right, I need to hurry along now because I'm running out of time. But anyway, so just in summary for that performance testing, we've now got robust evidence, statistical evidence to show what properties are salient properties of erosion control geotextile. The ground cover, the water holding capacity, this geotextile induced roughness, the percentage weight when wet, and the depth of flow ponded. And we hope this sort of information is going to be useful by designers and manufacturers to make more effective products, but also will help specifier and contractors select the most effective product and challenge the manufacturer as well. What is your water holding capacity? What is your percentage ground cover? How wet does this product get when it's wet? And I think that's going to be useful for contractors to select the most appropriate product. And who knows, it might also help to set new designs, new materials in the future. And along those lines, I also wonder to what extent these factors are taking into account in national and international standards. And I'm very sorry to say they're not. I sit on this British Standards Committee for the use of geosynthetics for surface erosion control. And I'm really saddened to know that one of the specifications is about tensile strength, and our research has just shown tensile strength is not related to the performance of these products in controlling erosion. And I would argue that some of these standards should take into account these geotextile properties where we do have a relationship with performance, rather than something like tensile strength, which has no correlation to performance, to what these products are meant to do. Sorry, I'm sounding really like an angry old woman, aren't I? Apologies. I'm really sorry. She's getting very tired and emotional. Sorry. Anyway, I do feel very strongly about this, that it's got to be fit for purpose, and I do worry that sometimes we're not measuring the right things. All right, rant over. Okay. Just very quickly, I just thought I'd mention that, and I haven't got time to go into this now, but geotextiles are also really important, not only for controlling erosion, but also to encouraging vegetation establishment, which again, as environmental engineers, we want that vegetation up and running as quickly as possible to control erosion. So there is a lot of research, and we've done research, and I haven't got time to present it now, that different products are also able to establish vegetation very successfully on slopes, as well as controlling erosion. I'm happy to take any questions on that sort of outside the meeting if that's of use. I want to finish off now by presenting some work. So it's not just me sitting in my lab under my rainfall simulator, that this has got real life applications. And I just want to finish off with a case study to demonstrate the sort of work that we're doing with farmers and other partners in trying to control erosion problems. So this is a farm down in Herefordshire, beautiful part of the world, but horrendous erosion problems. But this farmer is very right on. He's really got the message that he needs to try and control the soil erosion on his land. So he's called us in. This is my colleague standing in this gully. This is Dr. Rob Simmons, a great colleague of mine. Used to be my PhD student years ago, many years ago. But anyway, and we're working with this farmer to try and solve some of these erosion problems. Basically, he's using the land for asparagus production, which is a highly erosive crop, very, very high. Forgive me for using an agricultural example, but the principle is the same. Very, very high erosion rates associated with this crop, high erodibility, lots of rainfall, steep slopes, all the no-nos in terms of erosion, and consequently he's got really bad erosion problems on his land, and all of his precious soil resources ending up in drains and on the roads. They have to close the roads, and the Environment Agency gets very cross with him. So what we've done is to use our knowledge about geotextiles to help him build grassed waterways in his field. So this is the sort of typical problem in the top left-hand corner of these gullies, these erosion features. And we've then designed the width and capacity of this channel. We've lined the channel with a natural fibered geotextile to control the erosion in the short term. This is what the geotextile looks like once it's been laid down, encouraging the grass to grow through that geotextile, so controlling any erosion, any runoff that is actually coming off the land. And the geotextile will do that itself in the short term, but once you've got that grass, you've got this composite control of erosion and runoff, and it works very, very well. And this is us going out with some students to actually evaluate the effectiveness of that grass waterway with the geotextile. And again, the point I'm making with this table is a rather fussy table, but just to demonstrate, because the farmer is very concerned about the amount of land he's losing when we come along and say, you've got to have a grass waterway in there to control erosion. He said, oh, that's taking up a lot of my land, I don't want to. So we say, but if you put a geotextile lining, you will bring down the width of that channel because of the roughness imparted to the flow. You can have a deeper channel but a less wide channel, which means you're going to have much less land take than where you have the same feature, grass water bay, but without a geotextile lining. And that's all to do with this roughness imparted to the flow, allowing you to have a much more efficient channel, which will take up much less room, but still control the erosion and runoff. So my take-home messages, in summary, and to wind up to allow some time for questions, hopefully. So the demand for soil erosion control geotextiles is likely to expand, not least because of urban development, but also because of climate change and erosion risk. Geotextiles are very effective at controlling erosion immediately. They may enhance vegetation establishment as well to get these long-term synergies. I would argue erosion process is really important to understand those and how the products will interfere with those erosion process and interrupt those erosion processes. I would argue, wouldn't I, lab trials, we still need much more field validation. We need more robust data at the field scale. There's a lot of interest in biodegradable, environmentally friendly products because they are sustainable, they're renewable resources, and they may contribute organic matter, carbon. We hear a lot about net zero carbon and so on, nutrients and biodiversity. And as I say, there is an increasing database on geotextile effectiveness, but we still continue to try and develop that evidence base to help the industry specify these products. So with that, I will I'll draw my speech to a close, and I'll be delighted to take any questions. Thank you very much.
Thank you, Jane. That was a fantastic presentation. I think we've all learned something from that, and we do have a few questions, and we've got a bit of time as well. So the first question that we have is what method is used to capture and quantify sediment losses or presence in flows, and what are the common methods that you use there in the UK?
So my understanding of the question is how do we actually measure the sediment concentration within flows? How much soil is actually in the flow? Is that the right question? Yeah, I think that's what the question's aimed at. Okay, so in my lab trials, what I do is I take the runoff with the sediment within it, and then we just simply filter. We take a subsample and then we would filter it. I have used flocculation agents where you basically agitate the runoff and the sediment together and add a flocculant, and then the idea is that the sediment drops to the bottom. But again, then you need to still separate the runoff. You can decant the runoff and then evaporate or slowly dry out the sediment to collect it. In the field, we have taken sediment samples, sort of pipette methods of actually taking a water and sediment sample. But again, we then need to separate the water and the sediment. We usually do that either by filtering or by evaporation. Great. All right. Thank you. I hope that answers the question.
Yeah, I think that's pretty clear. Another question we've got is, have you done any work to look at the use of geosynthetic options in stormwater channels versus traditional riprap lined options?
Many years ago, I was involved in a project that was run by the Construction Industry Research and Information Association, Syria, that looked at different dam spillways. It was called the Jack House Reservoir Trials. And there they were looking at different dam spillways and different linings from nothing through to riprap, through to concrete block structures, through to geosynthetics. And they identified the critical flow velocity at which those different linings failed. Yep. So there is a publication. So we were involved in that publication, and they were looking at shear stress, shear strength of the different products and critical flow velocities at which those products failed. Yeah. I haven't been involved in that for many years, but there is that is kind of a bit of a Bible of a manual. I suspect it's only available in the UK, but
I think I've seen the document. There's like a chart, and there's concrete and
yes, you're right. Yes. I thought you were going to say I've seen the document. It's green, isn't it? But no. Yes, you're quite right. It's critical velocity and I think it's duration of flow, isn't it? Something
Yeah.
like that. And it's the critical point at which they fail. Yeah.
One question regarding the case study at the end there. So the channel that was created, do you know specifically what type of grass was used there?
I don't, but I could certainly find that out. It will be probably a mix. It will probably have some ryegrass in it, which will get going very quickly. It will probably have some fescues, some timothy grass. I've probably got the specification somewhere, but something that grows jolly quickly, but then also something that has quite a rigid stance. What you don't want with grass is sorry, I should do it that way. What you don't want with grass is to fall over. What we found actually in the Jackhouse reservoir study was that you need very short grass, so you have to cut it. If it's too long, with the flow, it will then fall over, lodge, and that actually increases the flow velocity. So there was some really nice work done on that to look at velocity of flow with short tufty grass versus very long. You'd think the long stuff would be good, but it isn't by the time it falls over. But I can find the grass seed spec. It will be a fairly standard spec.
Yeah.
James, a lot of our audience actually like the word huggability. So like that.
All right, I will. I'll change my present. I'll change the drapeability to huggability. But yeah,
we'll see a few specifications.
Yeah.
And as a designer, Jane, we I'm one of those who actually put tensile strengths in my specification. And I know I note your comment about it, and I sort of agree with that. The only sort of place where it becomes important is when they mow the lawn, and some sites they do it very frequently, especially in the area that we are in, quite tropical or semi-tropical. So yeah. It's just more to deal with the tension or tensile stresses from the machinery used for the lawn mowing.
Absolutely, and I totally agree with that. And I probably didn't make it clear enough, but my point was that in terms of erosion processes, surface erosion processes, I know that if you've got a stormwater drain or a channel where you've got very high stress flow, then tensile strength may come into it. But I'm not talking about a high velocity channelized flow. I'm talking about surface overland flow erosion. So certainly if you're talking about a deep channel with high shear stress, high flow velocities, then tensile strength will be relevant. But for dry slope applications for erosion control on dry slopes, cuttings, embankments and so on, I don't think it is necessary. Apart from handling onto site, it doesn't correlate with those erosion processes I've mentioned. Yeah.
Sure. We have one more minute, maybe one last question, Ryan.
Yeah, one more question. So this question, gradient will impact on the infiltration rate. So steeper gradient should result in less infiltration and greater runoff. What was the basis for selecting the hydraulic gradient used in the performance testing, as no measurement of soil moisture was presented?
So gradient, I assume this means the lab tests. So the gradient we chose was just a uniform gradient. We've used different gradients. I think we've gone up to 25 degrees in the most recent product evaluation trials. And we were trying to be representative of construction sites and slopes. So field work, we have gone on steep slopes where we've actually gone onto highway embankments and actually carried out some field evaluation. So it was really trying to choose a representative site, a representative slope. I take the point about gradient will affect infiltration and indeed performance. So I'm sure if we looked at different slopes, then we might get different performances, but that was one variable that we kept constant. But we can do them all over again at different slope angle. That wouldn't be a problem. Yeah, yeah.
Okay. We do have quite a few more questions, but if we could maybe email those to you, and we can get back to the people that ask those questions, if that's okay.
Yes, that's not tonight though, if that's all right.
No, I think you've well, due to go to sleep now, I think.
I think so.
Yeah. So
one of them, Jane, is a research topic that is potentially going to be future work for yourself and your team. So we will email them through.
Please do. I'd be delighted. Yes, and I'd be more than happy to answer any questions. And if anything comes up later, again, please give people my email address. I'm happy to enter that discussion. Thank you very much, Jane, and thanks for being available to us again at the early hour morning now in the UK. So it's very much appreciated, and we've had a fantastic response from the audience from today's presentation. So thank you. My pleasure. My pleasure. Thank you very much. Okay, so have a good day, everyone. I'm off to bed. Okay, thank you. So the details of our next webinar, they'll be sent out via the bulletins on LinkedIn very soon. And yes, thank you everybody for attending, and see you again next time, and enjoy the rest of your day. Goodbye. Bye everyone. Bye-bye. Bye.